Hey there, it's Shannon Matchick-Myers, and today we're going to be checking out chain rules for functions of several variables. So let's go ahead and warm it on up. A conical tank with the vertex down is 10 feet across the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. So why don't you practice your amazing related rate skills from your Calculus 1. Are you ready? On your mark, get set, go. I know you can do it. All right, let's see how you did. So what do we have going on here? We have this conical tank, right? Something like that. I don't like that one so much. Alrighty, and then you've got your radius, and that of course is your radius when full, right? And this here would be your height when full. But at any given time, couldn't you have another situation? I mean, you could have, as we're filling, you'll have a similar triangle. Whoa. You'll have a similar triangle that's created. Make sense? So, if you take a look at, we know that this whole amount was given as 12 feet when full, right? And we also know that the diameter, right? So this right here is the diameter, which is equal to double the radius, right? So this radius here will be 5, and it's all in feet. Now, at this, in the purple, we're simply going to have some general R and H. So, here we go. We know in general that the volume of a right circular cone is going to be 1/3 times pi r squared times h, right? So let's see what else we were given. We were given that water is flowing into the tank at a rate of 10 cubic feet per minute. So what we've been given here is the instantaneous rate of change of volume with respect to time, right? So that's going to be 10 feet cubed per minute. Now notice that we want to find, right? So this is what we've been given. We want to find the rate of change of the depth of the water when the water is exactly 8 feet deep. So when the water has filled the cone to 8 feet deep. We have that depth, and we want to know the rate of change of the depth instantaneously. So we basically want the instantaneous rate of the height with respect to time. This is what we want exactly when h equals 8 feet. That's the goal here. That's what we want. So we want DHTT. So let's check it out. Unfortunately, we have not been given, so we want this. We have not been given dr dt. So let's use similar triangles here in order to write r in terms of h. So if we do, big triangle is to small triangle as big triangle is to small triangle, we would have the height when full is equal to the height at height h, right? And the height when full compared to the height of the small triangle is going to be equal to the radius when full as compared to the small triangle. So that would give us 12r is equal to 5h, and we want to isolate r. So we would end up getting r is 5/12 times h. Cool so far? So now we have all the pieces, and remember, when you are finding a related rate, you don't want to plug things in too quickly. We will be plugging in r equal to 5/12 h into the volume formula, but we're not going to plug in the value for h or dv dt until after we've differentiated with respect to time to get the rate. So our volume will be 1/3 pi times 5/12 r, the quantity squared, times h. So all I did was, we had found this for r, and sorry, I believe I said h and I wrote r. So r is 5/12 h. And so this is what we're plugging in for r. Cool, cool? All right, so next up we have our volume will be, let's see, 25 pi over, I'm just going to write it as 3 times 144, you'll see why in a couple minutes, times h cubed. So when I differentiate with respect to time, the 3's will end up dividing out. So now ddt will have dv dt, which is something that we've been given, and that's going to be, remember these are all constants, 25 pi over 3 times 144 times, we've got 3 times something squared times ddt of our something using the chain rule. And what was that something? That something was h. Beautiful. So now we can divide out these 3's, and we'll have dv dt will be equal to 25 pi over 144 times h squared times dh dt. Cool so far? Awesome. Now remember that we have values for dv dt and dh dt. So let's go ahead and substitute those in and simplify. So dv dt was 10 feet cubed per minute, and so I'm just going to put in we'll put the units in at the end, and that's going to equal to 25 pi over 144 times, we're interested when that depth was 8 feet, And then our unknown is the dH dt. So we were given, or we're looking for dH dt. We were given, dV dt, and then our H was 8 because of this line when the water is 8 feet deep, right? And let's see what we got. So we will get, just, starting to do some of the math, we'll have 1440 over 25 pi, and then that's going to be times 64 is equal to dH dt. And so let's just get an approximation for that. If we approximate that, I believe we will get all right, so I ended up getting about 0.2865. So we'll end up with dH dt is approximately 0. Let's just go to the nearest hundredth, 29. And that would be in feet per minute. Cool, cool? And since it's positive, then our water level is going to be increasing by that amount. If we had gotten a negative, like if the water had been flowing out or something, then we would have gotten a negative, which is fine. It would have meant it was going down by that much. Cool, cool? All right, so let's get going. Theorem, the chain rule for one independent variable. So let's say you've got W is equal to some function of x and y, where f is a differentiable function of x and y. Sorry. If x is equal to g at t and y is equal to h at t, where g and h are differentiable functions of t, then w itself is a differentiable function of t, and dw dt is equal to the partial derivative with respect to x of dx dt plus the partial derivative of w with respect to y of dy dt. So this can be extended to any number of variables. So let's say w is equal to f of x1, x2, down to xn. You'd have sorry, there was an error. You'd have the regular d's here. dw dt is equal to partial derivative of w with respect to x1 of dx1 dt plus partial derivative of w with respect to x2 of dx2 dt, all the way down to the partial derivative of w with respect to dxn of dxn dt. So that's how it would extend. And let's take a look at an example. All right. So we've now got A. or example 1, we want to find, and again, I'm sorry about the notation. I thought I got all of these arrows. This should just be these regular D's, dw, dt. And so we want to find dw dt. First off, using the appropriate chain rule, and second, by converting w to a function of t first and then differentiating. So, we're just going to experiment. So the first way would be dw dt would equal to the first partial derivative of w with respect to x of dx dt plus the first partial of w with respect to y of dy dt. So let's do it. We've got dw dt is going to equal to the first partial of w with respect to x of what was dx dt? Beautiful. That's going to be 2 times t. And then plus the first partial of w with respect to y of dy dt. Well, what's dy dt? Awesome. 0, because y is equal to 1. It's a constant. So now dw dt, the derivative of w with respect to t. So now dw dx, the first partial derivative of w with respect to x. Remember, w is cosine at x minus y. So we're going to get negative sine at our something, that's differentiating the cosine part, and then times the derivative, the first partial derivative with respect to x of that something. And what was our something? Remember, it was x minus y, and so this would be here. And we still have that 2t hanging out, right? So then we'll have times 2t. And then remember that we're multiplying the first partial of w with respect to y times 0. So that would end up just being 0, right? So I'll just write that in. That would be plus 0. So continuing, we will have dw dt is equal to negative 2t times sine at x minus y, and then the derivative with respect to x, or the partial derivative with respect to x of x minus y, is just going to be 1. And we've already put in the 2t. Now we just need to substitute what x is in terms of t. All right? So dw dt will be equal to negative 2t times sine at x was equal to t squared and y was equal to 1. So this, whoops, sorry. This was y, and this was our x. Cool, cool? And we're all done. So now let's take a look at doing this where we first write it in terms of t. So here we go. W, So this is the second way. W would equal to cosine at t squared minus 1. Again, doing the same substitution that we had just done previously. And if we evaluate the derivative with respect to t of both sides, then we will have dw dt is equal to, again, derivative of the cosine is going to be negative sine of our something now times ddt of that something. So what was that something? It was t squared minus 1. So continuing, we will have dw dt is equal to negative sine at t squared minus 1, and then the derivative with respect to t of t squared minus 1 is 2t. And putting it all together, we'll get dw dt is equal to negative 2t times sine at t squared minus 1. Cool, cool. So fortunately, we got the same thing. It's a good day. All right. So for part B, let's check that one out. Actually, why don't you go ahead and pause the movie and try that one on your own. See how you do. I know you can do it. Ready? Pause the movie. On your mark, get set, go. Okay, so our new way is doing it how? dw dt is equal to the first partial with respect to x of our w. Actually, let me write it here so it's nicer. And then times dx dt plus our first partial of w with respect to y, dy dt, plus our first partial of w with respect to z times dz dt. Good so far? So actually, if you want, we can do the derivatives real quick. Well, you can see them. They're not real hard. So here we go. So dw dt will be equal to the first partial of w with respect to x of, and so dx dt, again, I think is the same, just 2t, because x was t squared, plus the first partial of w with respect to y times dy dt will be, beautiful, just 2, and the first partial of w with respect to z, dz dt. dz dt, remember you need to differentiate the power, so that's negative 1, and then we get times e to the negative t. All right, so now we do the partials. So dw dt is going to end up being, now remember, we're now working with w equal to x, y, z. So when we do the partials, two of the variables will be treated like constants. So the first partial with respect to x is just going to be y times z. And then we still have our 2t from before. First partial with respect to y is going to be x times z. And we still have our 2 from before. That's a 2, not a z. And then our first partial with respect to z is going to be xy. And then from before, we have our negative e to the negative t. Now, what we want to do is write everything in terms of t, correct? So dw dt will be, so y was 2t, z is e to the negative t, and then we have another 2t from before. I keep making them look like z's, 2t. And then plus, so x was t squared, and z is e to the negative t. And we had a 2 already. And then we have xy, so we'll have t squared times 2t. And then we had negative e to the negative t hanging out there. So if we go ahead and combine like terms and factor out an e to the negative t, we will get dw dt. Do you see that the very first one we have 4t squared e to the negative t, and the second one we have a 2t squared e to the negative t? So actually I'll just factor as it is. All of them have a factor of 2t squared. So we can have 2t squared times e to the negative t. And the first one, we have an additional 2. The second one is just going to be plus 1. And then the third one is going to just be minus t. So at the end of the day, dw dt is going to equal to 2t squared times e to the negative t times 3 minus t. Cool, cool? Alrighty. So now doing it the old way, let's see what'll happen. And actually, just so you can see how we got everything over here. And then our x was t squared. And then our z was e to the negative t. Good. All right. So now we're going to write w in terms of t to do it the old way. So w will equal to x times y times z. So you'd have t squared times 2t times e to the negative t. So w would be 2t cubed times e to the negative t. Differentiating with respect to t, we will have dw dt. We have to use the product rule. So this is going to equal to 6t squared times e to the negative t plus 2t cubed times negative e to the negative t. Factoring out a 2t squared e to the negative t, we will have 3 minus t. And fortunately, again, that is the same thing we got doing it the other way. Groovy? All right. So now, here is if you have two independent variables. So let's say w is equal to some function of x and y. F is a differentiable function, where f is a differentiable function of x and y. But this time, instead of just x equaling to g of t, we have x equaling to g of s and t, and y is equaling to h of s and t, such that the first partials, first partial of x with respect to s, first partial of x with respect to t, first partial of y with respect to s, and first partial of y with respect to t, all exist. Then it turns out that the first partial of w with respect to s and the first partial of w with respect to t exist and are given by. So the first partial of w with respect to s is equal to the first partial of w with respect to x times the first partial of x with respect to s. So we'd have this here. And then plus, we'd have the first partial of w with respect to y times the first partial of y with respect to s. So that's our dw ds, and our dw dt will be dw, first partial of w with respect to x, times the first partial of x with respect to t, plus first partial of w with respect to y, times the first partial of y with respect to t. Let me move that over for you. There we go. Okay, cool so far? Now, it also turns out that this can be extended to any number of variables. So I'm not going to talk through all of that here, but it's written out for you at the bottom here of the box. So let's work with it. Let's find first partial of w with respect to s and the first partial of w with respect to t using the appropriate chain rule, and evaluate each partial derivative at the given values of s and t. Cool so far? Okay, so here we go. What are we going to need to find? Let's see. Let's go ahead. Let's go ahead and find some of these different things. So on the right side here, we know we're going to need to find what? Good. We're going to need to find the first partial of w with respect to x, the first partial of x with respect to s, and the first partial of w with respect to y, and the first partial of y with respect to s. So we have a kind of a laundry list of things to find. So here we go. So the first partial of w with respect to x is going to be, remember, we'll be working with w right here. So basically we will be treating y as a constant. So let's see, the first term would zero out and we'll end up with negative 6xy. Good with that? Okay, good. And then let's go ahead, we'll continue with w and then find the first partial with respect to y because we're going to need that. And so now x would be treated as the constant. So we would get what? 3y squared minus 3x squared. Good so far? Awesome. Now dx with respect to s will be beautiful, e to the s. And let's go ahead and look at dx with respect to the first partial of x with respect to t, and that will just be 0, right? Because we don't have any t's in e to the s. So dy with respect to s will be 0, and the first partial of y, rather, with respect to t will be e to the t. Good so far? All right, so we've got all those partial derivatives. So now we know that in general, dw, the first partial of w with respect to s is going to be the first partial of w with respect to x times the first partial of x with respect to s plus first partial of w with respect to y times the first partial of y with respect to t. No, sorry, s. That'll be the next one. So, plugging in what we have, we're going to have the first partial of w with respect to s is equal to, so we got dw dx was negative 6xy, and then that was first partial of w with respect to x, negative 6xy. I'm going to just call that del, okay? And then del x with respect, first partial of x with respect to s was beautiful, e to the s. Continuing, we'll first partial of y with respect to, first partial of w rather, with respect to y was 3y squared minus 3x squared. And the first partial of y with respect to s was 0. Cool so far? So, how did we get all these? So here was our dw dx. Our dw dy is right here. Dx ds was our e to the s, and dy ds was 0. Cool, cool? All right. And so dw ds, let's go ahead and write everything in terms of s and t, all right? So we would get negative 6 times e to the s, because that's x, and then y is e to the t, and we still have this e to the s hanging out from the derivative, plus the rest of it zeroes out. So, how does this match up? We have x was e to the s, and then y was e to the t. And so, our dw ds is going to equal to negative 6 e raised to the 2s plus t, because they're all being multiplied together, and then evaluated at s and t equal to 0 and 1, what would we have? We would have negative 6e to the 2 times 0 plus 1 would be just e to the 1, right? So just negative 6e. Groovy? Okay, so now I guess I'll have to, let's add another page. So now for our first partial of w with respect to t, that's going to equal to dw, the first partial of w with respect to x, times the first partial of x with respect to t, plus the first partial of w with respect to y times the first partial of y with respect to t. So we will have first partial of w with respect to t is, we've got all this stuff, right? So we'll get negative 6xy, and then what's dx dt? That's going to zero out this time. And then we'll have plus 3y squared minus 3x squared. And then our dy dt is e to the t. So here we go. Our dw dx was here. Our dw dy was here. And then some new ones. We've got dx dt was 0, and then dy dt was e to the t. All right, so now we'll have the first partial of w with respect to t will be first term zeroes out, and then plus, if I'm going to factor out a 3, y squared is going to be careful with your exponents, we'll have e to the t squared minus e to the s squared. And then we still have the e to the t hanging out. And where did we get this stuff? We got it as x was e to the s and y is e to the t. So then the first partial of w with respect to t is, we'll have 3 times e to the t squared is e to the 2t, and then minus 3 e to the 2s, all of that's times e to the t. And I think I'll just keep it like that, because remember, we're plugging it in at 0, 1, where s is 0 and t is 1. So let's see what we'll get. We'll get 3e to the 2t So this would just be 3e squared, right? Minus 3e to the 0. 2 times 0 is 0. And that would be times e to the 1, right? So that would just be, again, I can factor this 3 out. And I can factor out, well, what do we have? We have a 3 times a 3e times e squared minus 1 when we pretty it up a bit. Cool, cool? All right. So there we go. We've gotten very far. So now we just have, I think, a couple pages left. So let's take a look at implicit differentiation with the chain rule. So if the equation capital F at xy equal to 0 defines y implicitly as a differentiable function of x, then dy dx is equal to negative fx x and y over fy x and y, as long as that denominator is not equal to 0. Now, if you've got an equation f at x, y, z equal to 0, that defines z implicitly as a differentiable function of x and y. If that's true, then dz dx will be negative fx xyz over fz xyz. And the first partial of z with respect to y, so actually it was the first partial of z with respect to x was the first one. First partial of z with respect to y would be negative fy xy and z over fz xy and z. As long as, of course, fz xy and z is not equal to 0. So let's check it out. We'll do a fun one that's got lots of trig. So differentiate implicitly to find dy dx. So here we go. Let's just see what kind of pieces that we have, right? So here, do you see we have a function of x and y, and we've got it equal to 0? So here we go. So that would give us that we have f of x and y is equal to cosine x plus tangent at xy plus 5, and that's since that f of x and y is 0. Cool, cool? All right, so what do we have going on? Beautiful. We want to find dy dx, right? So we know in general that dy dx is going to equal to the opposite of the first partial derivative of f of x and y with respect to x over first partial derivative of x and y with respect to y. So let's see what we get. Well, so this will be dy dx is negative. So fx of x and y, treating y as a constant, means that we will have, beautiful, we'll have negative sine at x for the first term. We will add to that, beautiful, y is treated as a constant, right? So using the chain rule, we'll have y, and then what will we have? We'll have the derivative of tangent of something is secant squared of something, and what's our something? Our something is x times y, and then the plus 5 zeroes out. So in our denominator, we will have, so now treating x as a constant, our first and our last term will zero out. And so again, using the chain rule, we're going to get this time x times secant squared of our something, and our something is x times y. Cool so far? All right, and then prettying it up a bit, let's see what we'll have. So this will be a final result of dy dx is equal to, so bringing that outside negative into the numerator, that would end up giving us positive sine at x minus y times secant squared at xy over x times secant squared at xy. We're done. Good, good? All right, so example 4. Why don't you guys pause the movie and give this one a try, see how it goes. All right, let's see how you did. We've got to find the first partial derivatives of z. So here we go. You got to be careful. We want to get it equal to 0. So this would be x times natural log at y plus y squared times z plus z squared minus 8 equals 0. So that's going to give us capital F of x, y, and z is equal to x times natural log at y plus y squared times z plus z squared minus 8. Cool, cool? All right, so now what we need to find, and I've got room in the next page as well, so we need to find dz, the first partial of z, with respect to x. And then we'll need to find the first partial of z with respect to y. So this first one is going to end up being negative. So we'll find the first partial of f of x, y, and z with respect to x over the first partial of z, first partial of x, y, and z with respect to z. And let's see what we get. So this will give us dz dx, or sorry, the first partial of z with respect to x is negative. So treating y and z as constants, we'll just get natural log at y for the first term. The second term will zero out, as will the third and fourth. So that was easy, right? And so then we will have in our denominator the treating x and y as constants. The first and the last term will zero out, and then the second term will just get y squared, and the third one will have plus 2z. Cool, cool? And that's our result. We don't really need to clean that one up, so I'll box that one. Okay, so now the first partial of z with respect to y is going to be equal to negative, and then the first partial of f of x, y, and z with respect to y over the first partial of x, y, and z with respect to z. So that will give us negative. So now treating x and z as constants, we will have, I believe, x over y for the first term in the numerator. And then we will have plus 2yz, and then the other two would be constants, over, that'll be the same denominator as we had before, right? So we'll have y squared plus 2z. But let's clean this up a little bit, because we've got a complex fraction going on. So if we multiply by y over y, then we will have, if you need to, put y over 1 over y over 1 to line it up. So then we will have dz, dy, the first partial of d with respect to y will be, we've got that negative on the outside, and we'll get x plus 2y squared z over, we can keep this y factored out, and it's times y squared plus 2z. And we're done. And so actually, we didn't even need the extra space. All right, so our last example here is kind of similar to our first one. We are going to use our advanced skills about this one though, right? So the radius of a right circular cone is increasing at a rate of 6 inches per minute, and the height is decreasing at a rate of 4 inches per minute. So what are the rates of change of the volume and surface area when the radius is 12 inches and the height is 36 inches? Okay, so what rates are we given? Beautiful. We're given the first partial of r with respect to time is 6 inches per minute. And we're given the first partial of h with respect to time. It said that it's decreasing at a rate of 4 inches per minute, so it'll be negative, okay, 4 inches per minute. Cool so far? Let's see, what else do we know? We know that the volume of a right circular cone is 1/3 pi r squared h. And just in case that you didn't know the surface area, so the surface area for the cone turns out to be pi r squared plus pi r times h squared plus r squared to the 1/2, or the square root of that. Okay? All right, so let's just kind of truck along and figure out what all we need, right? So here, so for the first one, rates of change of the volume, right? So we want dv dt. So finding dv dt all right, so dv dt is going to be, so from our formula we have our dv dt equals 1/3 times, now differentiating, we're gonna need to use the chain rule, right? So it's actually going to be pi over 3 because that's a constant. And now we've got this r squared h part. So we're going to end up, let's go ahead and just take a look at it as the first partial of v with respect to r, and then times dr dt, plus the first partial of v with respect to h times dh dt. Good so far? All right, so here we go. dv dt will be pi over 3. Now, looking at v and keeping r as and treating r as the variable and everything else as the constant, so h would be a constant, what are we going to have? We're going to have, beautiful, 2rh. And then we just have our dr dt, which we know it's given. And then the first partial of v with respect to h. So now treating r as the constant, we're going to have, beautiful, just r squared. And then we have our dh dt. And remember, we have that value. Cool so far? Perfect. So now we'll have dv dt is equal to pi over 3, and we're interested in all this happening what when r is 12 and when h is 36, and those are both in inches, right? So plugging in 12 for r and 36 for h, and then dr dt was 6, and then again over here we'll have 12 squared this time, and dh dt is negative 4. So it's for the r's. Here's for the h's. And then we have rates, so dr dt and dh dt. All right, so putting it all together, dv dt will be equal to pi over 3 times what? Get the calculator out. So I get 4608 here. So then dv dt will equal to, so if I divide that by 3, we get 1536. So exactly 1536 pi, and that's in inches per minute. So this would be inches cubed per minute. Cool, cool? All right, so these aren't too terrible. And next up, what do we need to do? We need to find the surface area, right? So for our surface area, looking at our formula, so our surface area would be d, and then we called the surface area SA, So dSA with respect to time is equal to the first partial and actually I'm going to factor out the pi because that's a constant in all of them. So we would have the first partial of the surface area with respect to r times dr dt plus the first partial of the surface area with respect to h times dh dt. Cool, cool? Okay, so working it out, we will have dSA dt is equal to pi times. For our first term, we factored out a pi, right? So we're going to end up having, we'll have a 2r. Now, the second one, what's going to happen, we're going to have a product rule. So we're going to have a 1 from differentiating the r times h squared plus r squared to the 1/2. And then we'll have plus r times 1/2 h squared plus r squared to the -1/2 times 2r. So that's just the first part where we are differentiating, finding the partial with respect to r. So, you know what? Let me move this over. I'm sorry. Let me move this over here so I can fit that other term. And we'll divide this. Okay. All right, so now completing it, we will have, so this is all of this one. And then all of that is going to be times dr dt. Okay. Now we need to do the same thing, but now we're finding the first partial of the surface area with respect to h. So the first term zeroes out, and the second one becomes much easier because we'll treat the r as a constant, right? So now what will happen is we will have r times 1/2 h squared plus r squared to the -1/2 times 2h. All of that is times dh dt. So this here is all of this. All right, so now let's clean it up. So we will have pi times, I'm just going to start plugging in. So remember, r was 12 and h was 36. So 2 times 12, and remember this will all be times dr dt, so can't forget the grouping, and then plus the square root of 36 squared plus 12 squared plus 12 over 2 times 1 over the square root of 36 squared plus 12 squared times 2 times 12. All of that is times dr dt, which was 6. Plus, now put the other one below. So r times a half again. So we'll have 12 over 2 times 1 over the square root of 36 squared plus 12 squared, and then times 2 times 36. All of this was times dh dt, which was -4. All right, so let's see what we end up with here. We can do a little bit of simplification here, I think. Let's do that before we plug it all in. Because, let's see here, these 2's divide out. And then these 2's divide out. All right, so cleaning it up a little more, we'd have the derivative of the surface area with respect to time is going to equal to pi times so we've got a 24 from the 2 times 12. 36 squared plus 12 squared is 1440. So we've got a root 1440. And then plus 144 over root 1440. And all of that is times 6. And then that -4, we'll make this a subtraction. And then we're going to have, what, 12 times 4 times 36. So we'll end up with, 1728, I did this right, over root 1440. And when all is said and done, you approximate this. The derivative with respect to time of the surface area is going to be approximately all right, so we end up with approximately 1096.15. And that's in inches squared, because we're in surface area, per minute. Cool, cool? All right, so that's it for today. Hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe and tell your friends. Bye.